Our next presenter is Ross Bonatine from VORAGO Technologies.
My name is Ross Bonatine. I'm representing VORAGO Technologies. Please excuse me. For those of you who are not familiar with our company, we are a privately held fabless semiconductor company based out of Austin, Texas. We've been going since 2004. In 2015, we changed our name from Silicon Space Technologies to VORAGO Technologies, and also placed a greater focus on commercializing the technology that we had developed over the previous 10 years. Much of that technology was developed under small business innovation research projects for Department of Defense. The technology that we created is known as hard cell, and it is a method to harden any type of CMOS device. And we do that by putting implants into a standard CMOS flow. So the benefit there is that we can run the products through a standard CMOS commercial fab that is dealing with high volume and high quality products. We also aim to leverage commercial IP, such as the ARM processor that we utilize in our microcontroller products. We have licensed the technology to several semiconductor companies, and we have created our own modest portfolio of memory and ARM-based microcontroller chips. The nice thing about using hard cell on CMOS is that it doesn't impact the performance of the transistors or the power consumption or the yield. Next slide, please. Oops. Okay, got it now. Let me explain a couple of minutes about our hard cell technology. What you see is a cross-section of a CMOS device, and it shows an NMOS transistor and a PMOS transistor, and this is the structure that is implemented in all of the commercial CMOS fabs. You would probably recognize it from a textbook. Now, on account of the architecture and manufacturing of CMOS, there is a byproduct of that process which gives you some extra features, which is millions of parasitic bipolar transistors that are embedded onto the CMOS wafer. And typically, if the device is operating under normal operating conditions with respect to temperature and electrical stress and such like, these parasitic devices that look and behave like a thyristor are typically not a problem. In the event of ionizing radiation, if there's a particle strike, there's a potential that the thyristor-like structure can become forward biased. And when that occurs, it creates a short circuit from VDD to VSS, and that condition is known as latch-up. So the primary purpose of hard cell technology is to prevent latch-up. We do that by putting in a couple of implants and an extra mask layer during the standard CMOS manufacturing process to implant high conductivity areas which have the effect of reducing the gain of the parasitic NPN and reducing the RP well resistance, and that prevents the parasitic network from switching on, and it's proved to be very effective in preventing latch-up. There are some other more conventional means that we use to complement the mitigating radiation effects, and those are we add an error detection and correction subsystem, and the way that operates is as the CPU fetches a word, it inspects it on a byte level. For each byte we can detect 2 bit errors and correct 1. So for a 32-bit word we can detect 8 and correct 4. in order to prevent the probability of a multi-bit error to flip bits within a single byte, we add a scrub engine, and the scrub engine operates autonomously off the CPU, and it steps through sequentially all of the memory and corrects any bit errors that it finds. So by the time a word is presented to the CPU, to the EDAC, the probability of having a multi-bit error is vanishingly small. There's some other things that we do with layout. We space out logically adjacent bits so that a low angle of incidence strike does not take out more than a single bit within a byte. We also add some features to mitigate against single event upsets in the logic areas. And what we've done there is to replace all of the latches on the device with dual interlock cell latches, which have a 3 volt mechanism to prevent latches from being flipped from a particle strike. In addition, we do triple modular redundancy on the internal registers and add things like clock glitch filters to prevent single event transients from propagating through internal circuits. This is a block diagram of ARM Cortex M0 based microcontroller that we produce. It runs at 50 megahertz and has a basic set of microcontroller peripherals. This is used in quite a lot of CubeSat designs today and is flying. The radiation specifications are very strong. Total ionizing dose is 300K rads. LET is 110 MeV. It's effectively a latch-up immune, and the soft error rate is in the range of e to the minus 15 errors per bit per day. So really the radiation specifications are not compromised by the approach that we take, which is to use CMOS. We recently developed a design for a CubeSat OBC that is based upon the microcontroller that we just looked at. And what we tried to do was to find the radiation-hardened chips that we would use around as peripheral blocks around the microcontroller. So we added A to D from Cobham, it's a 14-bit A to D, radiation-hardened flash memory from Cypress, and there's COTS equivalents of those particular parts, incidentally. The power management devices are rad-hard from Intercell. And there's a couple of chips on there that are not rad-hard. There's a USB chip, which is not intended to be used in orbit, and we disconnect that chip during flight. And there is a combined CAN controller and PHY, which is not rad-hard, and we monitor the power supplies and voltages and currents and disconnect those power supplies in the event that the chip appears not to be working properly. This board is available through Pumpkin and is supported by Bright Ascension Flight Development Kit. Typically, we see our micro being used in a configuration such as the OBC that we just looked at, where the M0 is the main controller. Quite often, an ARM Cortex M0 running at 50 megahertz is not powerful enough to be a main controller in some systems. And the other configuration that we often see is as a watchdog or a monitor chip for a more powerful processor. In this case, the picture on the right-hand side of the screen is a Vertex 5 FPGA. It's a commercial COTS version of the FPGA, and that particular customer uses the VORAGO Micro as the rad-hard anchor chip to monitor, load, reset the FPGA and ensure that it behaves itself. So it's like a radiation-proof safety monitor that's been added to the system. We like the ARM Cortex M0. The power consumption is inherently very good. We've done a lot of work on how to reduce that power consumption further by gating off peripherals that are unused. and figuring out the peripherals that are responsible for using up the power budget of the device. The other thing we like about ARM is that there's a lot of software already available, so there's a lot of support for compilers, debuggers, real-time operating systems and such like, ranging from free to expensive, but it's well supported, so we enjoy that about the chip. Before I invite questions, I would like to say we are exhibiting here downstairs, and it gets kind of lonely down there, and I'm here all day tomorrow myself, so please come and say hello and help the day pass more quickly for me. I'd be delighted to see you. And I'd be also delighted to take any questions. Hopefully that doesn't mean that you couldn't understand my Texas drawl. Thank you very much.